Okay, NG. Yeah, it's a 3x3 matrix. So, no idea. Instant. You have a perfect camera, which means that what you have in the object space is, and after you take a photo, then it will be exactly the same as what you have in the object space. So your image will be exactly the same with the object space situation. You mean taking the photo from a different angle will cause some problem? So, like I said, if you view it from the same angle, yeah, doesn't matter if it's from different angle or not. So, if you see, for example, this pen from this angle, and that's what it's supposed to be. So, how black that is and how white that is fixed already. And if I use a camera to take the photo, then the image that I want it to represent what it should be in the object space. For example, I want to know what's the black over here, what's the white over here, then it will be exactly the same as what you have in the object space. Okay, so that's my question. And what's the point square function for such perfect camera? Deborah. Doesn't matter. It doesn't matter. The object. What's the situation in the object space? Doesn't matter. Just if you have a perfect camera, and that point square function of a perfect camera is what? Any idea? Right. Should be an easy one.
It should be like 0 equal to 1 quarter.
1 equals to 1.
I mean, supposedly, if it's perfect, then there should not be any modified or curvature, right? So the P is maybe like equal to P, the function of S and A should be equal to 1.
Should be, and how about others?
And S is perfectly kosher.
What?
The F is perfectly kosher. So
yeah. So should be
P should be equal to 1.
And then how about others?
There is others.
3x3, right? You have a 3x3 matrix.
So it's like the diagonal should be equal to 1.
So 1, 1, 1.
Yeah.
And 0, 0, 0, 0, 0. Any?
I'm
Okay.
not sure.
Any other idea? Oh, yeah. Not the cubic, actually. Not the cubic. Just a 3x3 matrix.
I think it's also one.
What's only one?
Because it doesn't have any deformation. So
Any change, yeah.
P is 1.
The pig is 1. And how about others? You have 8 other pixels, right? 8 other cells.
I thought 9 is in 1.
Mm-hmm. Oh, everything is 1.
Yeah.
Everything is 1. Okay. Any other solution? We have the diagonal as 1 and everything as 1 and any other things? Dude.
I have 7, 8, 8.
There.
The middle is 1.
And
the other is 0.
the other is 0. Okay, so we have the third idea. So middle is 1 and surrounding is 0. Alright, and any other idea? Any other solution? No? Okay, so we have 3 solutions. And which one is the answer? Which one is the answer? Alright, raise your hand if you think the diagonal as 1 and the others are 0. If you think that's the answer, please raise your hand. No? Alright, the second choice is 9 cells, they are all 1. Please raise your hand. 1, 2, 3, okay, like half of the class. Okay, the last one, the middle is 1, and the other surrounding 8 are 0. So if that's the answer, raise your hand. Okay, less. Okay, so the idea, well, the answer is this. The answer is this. So okay, so if you guys couldn't imagine that, then it may be because you don't really you don't understand how the convolution works. Right? You don't understand how the convolution works. So right, let's imagine. Right, let's imagine something like this. Actually, you guys should know it, like me. From other courses, okay, not from this one. But all right, let's assume let's just say 1, 2, 3, 4, 5, 6. Let's just assume that this is the F, this is the P, and eventually we will have an L. Something like this. So if right now, so the convolution means that we have a 3 by 3. So right now we are taking the convolution, and then it will be equals to this. So right now, if you are talking about the convolution, then what you are doing is you are going to put this convolution, this matrix to this location. To this location. And what you are going to calculate is the first cell, let's just say F00 multiply P00 plus F01 multiply P01 plus F3 multiply P, sorry, 2. Okay, so it will be equals to your L11. Right, so this will be the L11, this one. So the convolution it works like this. So for example, if you are taking the convolution on this matrix, and then you put this 3 by 3 matrix and on this one, and so you are going to multiply each of the cell and then take the summation, then you have your final result. And that final result will be the middle one, So the middle one, where is the middle one? Is over here. It will be over here. So, and then the next, so you decide one result, one cell for your result, right? One cell. And what's this L, right, let's say 1, 2, that's it. And in this case, sorry, 2, 1. L 2, 1. And this one is by taking the convolution on this. So you will move the matrix to the right for 1 pixel. You will move the matrix to the right for 1 pixel. And so, and then calculate the same thing, take the, multiply them and also take the summation. Then, so in this case, you will get another result, and so on and so forth. So you will move this window one pixel by 1 pixel to the right, and then to the bottom. So you go around and take the calculate the result for each of the pixel, and then you have your final result. Okay. So in this case, if right now we have, so supposedly you guys should have the idea right now already. So the camera, if it's a perfect camera, then it should be like this, because if you have a point square function like this, then what you have is you ignore every other things, the surrounding pixel. Whatever beside this middle pixel is not relevant. It's not relevant. So only the pixel that you care contribute 100%. Contribute 100%. So if this is the case, then this pixel will have 5, and this will have 6, and so on and so forth. Because you only have the middle pixel that influence the result. Okay? So that's the case. So usually, so what I'm trying to say is this is the perfect camera. But of course, usually usually any camera that is made by human and that is not perfect. So sometimes we will assume that the point square function follows, for example, a Gaussian. Follow a Gaussian function. Right? It follows a two-dimensional Gaussian function, and so that you still have a peak, which means that the middle pixel still contribute the most, but in the surrounding pixel contribute a little bit less, and then far away from the middle one contribute less and less. Okay, so it's like the Gaussian function. Okay, so sometimes we will use a Gaussian function to simulate the point square function. Okay, so hopefully this can help you understand the behavior over here better. Okay. Any question? Yes.
So that top from the final,
Yeah, you will become.
Okay, so then
You couldn't estimate that.
Oh,
Yeah, you couldn't estimate that.
So they will.
Yeah, it will become a little bit smaller. Yes, you will become a little bit smaller. So sometimes when you perform, after you perform the convolution, then you will see the edge that becomes black. Some people will just use black to represent that. But in reality, that means you couldn't estimate the value of that. And well, and also the size of those black is actually decided by the size of your convolution function. So, for example, if you have a 3x3 matrix, then you only have one pixel which cannot be estimated, cannot be calculated. So, but however, if you have a 5x5 matrix, then you have 2 pixels. 7x7 matrix, you have 3 pixels, and so on and so forth. So it's determined by, well, it's affected by how large your point square function is, or any matrix that you use in the convolution. Okay.
How about 4x4?
Can you use 4x4 or 6x6? Using why? Why not?
Because there are no central pixel.
Yeah, there is no center pixel, right? Because right now your purpose is to decide what's the outcome for the center pixel. So it should be the odd number, not the even number. Okay. 要占基数柔数。Okay, so any other question? Yeah. If not, then let's move on to how to calculate the MTF. If you do some search online, then you will find out there are many ways to calculate the MTF, and different people do different ways. For example, some people will take like second derivative on your image, the image that you take, and that works actually. That works. And usually, for example, like if you are creating a satellite or any certain camera system, then you want to understand the resolving power of that, then there will be some testing site or testing pattern that you need to take the photo. And after you take the photo, you are going to measure the differences between the differences between the white and black. And supposedly, you need to have you need to do your best to simulate a pure black and pure white, and there's a clear edge between them. And after you take the photo, then you are going to measure the changes in this cross section, in this you can say the digital count differences for that difference between from the white to black. So that's what people usually do. But however, you can here is the other way, but it's trying to represent the same process. So let's just say here, assuming that you have a test pattern over here, so you have black, white, black, and white. So sometimes you will see people have like a canvas. It's like a certain canvas, and then they will draw a big black cross over there, or it's like a chessboard. It will be like a chessboard shape. Then that is for the calibration purpose. That is used for the camera calibration. So especially for the camera, for the satellite camera calibration. So it will be a very large canvas, and then you will just lay it out in the flat area. And when the satellite go through this area and then take the photo, then because that canvas is created by you, so you need to make sure that the black region is a pure black and the white region is pure white. And so after the satellite take the photo, then you can start measuring because we know the ground truth. And then after we know the ground truth, and then we can try to measure the differences between your real image and your ground truth, and to estimate the MTF. Okay, so the idea is similar. So let's assume that the test pattern is this black, white, and black, white. And as you can see, here is a density trace. This is from some instrument called microdensitometer. It's measured from by the microdensitometer. In Chinese, it's called 微密度计. Right. So the microdensitometer is trying to measure how much light it has been absorbed for that region, for that location. For example, as you can see, this is the density. So this microdensitometer, it has the density trace. Then you can measure how much light has been absorbed for this location. So as you can see, the amount of light it has been absorbed is high. So the black region, it has a high value, and the white region, because there's no light has been absorbed, so the value is low. So like this. So high and low, high and low. So that is from the instrument called microdensitometer. Okay. But basically, it's measuring how much light it has been absorbed. In Chinese, we will call the 吸光度. How much light has been absorbed? 吸光就是光被吸走的那种光。